All right, Hess's law says, in going from a particular set of reactants to products, the change in enthalpy is the same, whether the reaction takes place in one step or a series of steps. Now, we haven't really studied chemical reactions that take place in multiple steps. That's really something that you'll study. You'll study the mechanism of chemical reactions really when you get to like organic chemistry, right? If you get to that point, you'll really go really pretty deep into how the reactants truly become the products, right? We've talked a lot about they trade electrons, they do that kind of stuff. That's pretty basic surface level type knowledge about what you need to know about chemical reactions. But in all reality, they happen in multiple steps, right? And they take multiple processes. Sometimes those processes go really quickly, but sometimes they take a little bit longer and it's multiple steps happening. And so when we look at chemical reactions, the change in energy from reactants to products is the same for a particular reaction, whether it happens in one step or multiple steps. And so we're going to start studying the change in enthalpy of these reactions if they take place in multiple steps. And we're going to look at the change of reaction in all of these different things. All right. Delta H1, right, they labeled it 1, is the change in enthalpy of the overall reaction, regardless of the number of steps. So if I look at my delta H value there, is that telling you that the reaction is endothermic or exothermic? Endo, right? My delta H is positive, which means it would be an endothermic reaction, which means we have to have heat go in for our reaction to take place. Okay, it's endothermic. But what happens is that the reaction actually takes place in 2 mini steps. So I call these mini reactions, okay? And these mini reactions are given here below, okay? What we're going to be able to look at is we have to figure out, like normally in most problems, this number won't be given, right? It will ask us calculate the delta H of the total reaction based on the 2 steps of the reaction, okay? And this is how we're going to actually do most of our problems. But most of the time, this number won't be given. And we're going to walk through how do we find out what's the total enthalpy change in the reaction if we only know the enthalpy of each of the steps, okay? Sometimes it's really easy, just add them together. And sometimes you have to do a little maneuvering to figure out, are the reactions going the right way and all that kind of stuff. That's what we're going to look at, okay? So we're going to go ahead and try this. Okay, we're going to try to prove that 68 kilojoules is the enthalpy of the reaction. Okay, so we're going to kind of just ignore this for right now. And we're going to try to figure out how can we prove that the total enthalpy of our reaction is 68 kilojoules. Okay, the first thing that I want to do is understand that this is the reaction we're aiming for these mini reactions to equal. Okay, some of these mini reactions include more things than we actually need. Okay, I want you to look through our final reaction here. N2, 2O2, and 2NO2. Those are the compounds that we need present in our final reaction. Does this first mini reaction, I'm actually going to label that number 1. Does it have any of those compounds? Does it have N2 or O2 or NO2? It has N2. And is it on the correct side of the reaction? Yes. Okay, so this one is good. Okay, what about this one down here? Does it have any of the things that we need? It has 2NO2 and it has O2. And my first one has O2 as well. Are the things on the right sides of the reaction, are they on the correct sides? Okay, so that means we don't have to reverse the reaction, okay? What I mean when I say that is that sometimes our reaction might be written like this. 2NO2, and it's a decomposition reaction. And if that was the case, our compound would be on the wrong side, and we would have to what's called reverse that reaction. Okay, we don't have to do that yet, so let's just go ahead and look at what we do have. If I look at my mini reaction, I'm going to need N2, I'm going to need O2, and I'm going to need 2NO2. Would we agree with that? Do I need the 2NO at all? I don't. It's nowhere in my final reaction. But now I want to see, does it cancel? Do these two cancel out? Yeah. Here's how we know if they cancel. They have to be on opposite sides of the arrow, right? One of them has to be a reactant, one of them has to be a product in order for it to cancel. The coefficients have to add up to be equal as well. So I can't cancel NO and 2NO, right? Those wouldn't cancel. They would reduce down, but they wouldn't cancel. Okay? So once I cancel this out, 2NO and 2NO, I'm going to basically just see what I have left. I've got N2. I've got how many O2s? 2. And I'm left with 2NO2. Does that look really similar to what I'm supposed to be having up here? Yes. And so because I've now reduced reactions, right? I've taken the mini reactions and removed the spectator ions. Remember what spectator ions are? Things that just watch, that don't take place, right? I've removed the spectators. I'm left with my final reaction. And so all I have to do is come over here and add these up. Okay, I'm going to take 180 minus 112, and I get a delta H value that's equal to positive 68, right? All I really did is prove that value. But most of the time, you won't have the value. Okay? We didn't have to do much rearranging here or solving here, but what our goal is to try is to get these mini reactions to look like our original reaction. So sometimes it's going to take more maneuvering, sometimes it's going to take less. But that's really our goal here is we have to maneuver these mini reactions to get them to add up to look like our final reaction. Okay? And then by taking these enthalpies of our mini reactions, we can add them together to find out the enthalpy of our total reaction. Okay. Go ahead. All right, let's look at the next one. If the reaction needs to be reversed, that means if we need to flip the products and reactants, that would mean that we would reverse the sign of the enthalpy for that reaction. Okay, so let me say that again. If we have to reverse a mini reaction, if one of our compounds is on the wrong side, and we need to reverse the reaction, we would take the delta H for that mini reaction and reverse the sign, right? If we're changing the way that the reaction is going, if it's originally endothermic and we reverse it, now it's exothermic, right? And so we would change the sign of that delta H value. The magnitude of delta H is directly proportional to the quantities of reactants and products. So the delta H that's shown is including all of the coefficients that are shown. So if we have to adjust a coefficient, we would have to adjust the delta H value. Okay, so if we would need twice as many of a compound, we would have to distribute that 2 through the delta H value as well. If the coefficients are multiplied by an integer, the value of H is multiplied by the same integer. That's what I just said. And if the coefficients are reduced or divided by an integer, the value of H is done the same. Okay, so all those ratios have to be kept intact. That's a fancy way of saying that, right? All of the ratios have to be kept intact. All right, let's look at this one. This is a simple one to start out with. It says two forms of carbon, are graphite and diamond, using the enthalpies of combustion for graphite and calculate delta H for this reaction. So this is our overall reaction right here. We're going from carbon, graphite to carbon, diamond. Okay, so we've got the subscripts really do make a difference, right? Graphite and diamond are two different types of carbon, so we've got to make sure that we're careful there. This is the equation that we're aiming for. So I'm going to look at my mini reactions down here and say, is this first one right here, is it in the right direction? Is it going in the right direction? It has carbon graphite as a reactant, so is it correct? What about the second one? Diamond's on the reactant side. So I like to just rewrite the whole thing, okay? I would rewrite it as CO2 breaks down to form carbon diamond plus O2. And then my delta H value for that reaction is no longer negative 396, it's positive 396. Okay, and then I want to make sure I cross out that middle equation. Okay, because I'm not paying attention to that anymore. Okay, if I have to adjust multiple mini reactions, I will just rewrite the whole set of them, right? So I'm not having to guess about which ones I X'd out, which ones I didn't. But I can pay attention now to just these two, okay? Now I'm going to pay attention to, I've got carbon graphite and carbon diamond, which is what I need. But now I need to figure out, are my extra things canceling out, right? Here's my arrow. Here's my arrow. Are my extra things canceling? Right? I have an O2 on the left and an O2 on the right, so those cancel. I've got a CO2 on the right on the left and a CO2 on the right, and so they cancel. Do you see how we have to cancel those opposite sides of the arrow? And so now I'm left with carbon graphite to carbon diamond, and so I just have to add up these things right over here. Okay, the important thing was that I switched the sign of that delta H. When I reverse the reaction, I switch the sign. So now I'm just going to take 396 minus 394, and I get a value of plus 2 kilojoules. To get a little more complex here. All right, let's look at the next one. Calculate delta H for the reaction. Okay, this reaction up at the top is the one that we're aiming for. Okay, yeah, you see how there's fractions? Ugly. Okay, not cool, but it's not so bad, right? We know how to multiply fractions. Okay, so here's our main reaction that we're aiming for. Okay, and here's our mini reactions. I like to go ahead and label my mini reactions 1 and 2, just so I have an idea. When I go to rewrite them later on, I kind of keep them as a set, but that's up to you. You don't have to do that. Okay. All right. I want to take a look at our mini reactions here. I want to see, are there any, first of all, that I need to reverse? Do I need to reverse either of them to begin? I need to reverse the first one. Will we agree? Is there anything else we can do right now, right? We can reverse and multiply by something. We could reverse and do that, right? Do you see anything else that is going to be an issue? We're going to have to get rid of the fractions. Okay, I could multiply by 2, but how many NH3s do I need? I need 4 of them in my reaction. Would you agree with that so far? So what I'm going to go ahead and do right now is I'm going to write an R and a times 4 by this first reaction to remind myself, what am I going to do to that first reaction? I'm going to reverse it, and I'm going to multiply it by 4. So I'm just making notes right now. On the second reaction, is there anything right away that we need to do, or should we just let it shake out for right now? I need, let's see here. I need O2 to be on which side? The product side. And I need H2O to be on the reactant side. So I'm going to have to reverse this one. And can you see, am I going to have to multiply it by anything? Can you look ahead yet? I think I need to multiply by 3 because I need 3 O2s and I need 6 H2O. So I'm going to go ahead and multiply that by 3. So I like to rewrite the whole reactions, right? I'm going to kind of draw myself a little line here. And I'm going to rewrite reaction 1, reversed, and multiplied by 4. So I'm going to start right here. What's 1/2 times 4? 2 and 2. I'm going to do a different color here so we can keep this straight. I'm going to go 2 and 2. The gas and liquid don't make a difference for us right now, so I'm going to leave that off. Sometimes it does, but right now it doesn't. Okay, and then I'm going to go 3/2 times 4. What's that? 6. 6 H2. And that yields 4 NH3. Okay, do we feel comfortable with how that got rearranged? Right, we reversed and multiplied by 4. So what has to happen to that delta H value? Yeah, we're multiplying by -4 essentially, right? We're going to switch the sign and we're going to multiply by 4. So 46 times 4 is 184. So we're going to go -184. All right, we feel comfortable with what just happened there? And we're good with the problem solving about how we figured that out? Okay, number 2, reaction number 2, we're going to reverse and multiply by 3. So it would become 6 H2O. And I like to put my arrows in the same spot, right? I want to try to line them up so I can really tell what's going to cancel, what's not. That's not the end of the world if you don't, but for me, it just makes the most sense. That would go 6H2 plus 3O2. My delta H value would then become positive 1452. Okay, how are we feeling about that so far? Does that seem like, does it make sense, the puzzle that we put it through, right? Reverse it and multiply. Now I'm going to check to see, do I have anything that I need? Right? I've got 2 and 2, which is what I need. I've got 6H2O, which is what I need. I've got 3O2 and 48H3. So then I need to see, do my extras cancel? What do you think? H2, 6H2, 6H2. So that means I'm good, right? And so then I just add those up. So 1452 minus 184 gives me a delta H value of positive 1268 kilojoules.